Okay, so what we're going to be talking about today is we're going to be talking about solubility product and versus solubility and also relative solubility. So how does that look when we actually start dealing with stuff? So first of all, let's define what solubility product is, and just a fancy way of saying KSP. And we already know how Ks work. Ks are essentially your products over your reactants, and it's always equal to some particular value at a particular temperature. So if we do, for example, if we had AgCl, and I keep on using this example because it's super fun, and it went to Ag plus and Cl minus, this being a solid, these both being aqueous, we know that if we wrote a KSP for this, the KSP would be equal to Ag plus concentration times Cl minus concentration. Yeah, and that'd be equal to some value, some number, and that would always be the same. What is solubility? In short, solubility is X. That's what solubility is. And typically when we're dealing with problems that deal with molar concentrations, and we can know that by the square parentheses, whenever we solve for X, it's going to be in molar or moles per liter, which is kind of a nice thing to deal with. Now, occasionally, they're going to ask you to solve for something in terms of grams per liter, but just be aware that X is what solubility is, and KSP is the K value, and specifically for when we're throwing a solid into water. Now, why did I start off with this when I'm talking about relative solubilities? Well, I want to show you something here. So sometimes what we have is we have a bunch of different salts. Salts are another way of saying ionic compounds, right? And each one of these, if you take a look, has a different KSP. Now, the KSP is how many ions you're allowed to have in solution, right? We can actually compare each of these salts via their KSPs, but we can only do that because they split apart into the same number of particles. And why is that important? Well, let's say we took a look at AgI, right? If we take a look at AgI, AgI when it breaks apart, doesn't it break apart into Ag plus and I minus? In other words, one particle of each of these. And if we were to write a KSP for this equation right here, wouldn't the KSP be equal to Ag plus concentration times I minus concentration? Yeah? And if we were to do an ice problem for this, which I had a little more space for, and if we did an ice problem for this, I'll slide it over here, wouldn't we end up with 0 and 0 for our initial, right? And our change, wouldn't it be plus X and plus X? And since we started off at 0, wouldn't it be X and X? So if we were plugging back into our equation, wouldn't this be X times X is, I don't know why I put an extra parentheses, equals KSP? So for all three of these, if I wanted to do the mathematics on it, it would be KSP is equal to X squared for all three of these. I'll put more arrows because that helps learning, right? So if solubility is X, and we just define it on the other page as solubility equals X, right? We don't even have to solve for X, because if all three of these, remember they all break apart into two particles, which means you're going to have X times X, which means you're going to have X squared. We can actually just compare the KSPs, and whatever KSP is the largest, that's the one that's going to have the greatest solubility. So of these three right here, since this is 10 to the negative 5, CaSO4 is going to have the largest solubility, which means more of it will dissolve than anything else, than any of these other three. Then you'll have CuI, and then you'll have AgI. So we can easily compare when you have the same number of particles that are being broken up into, we can compare our KSPs, and the KSPs will be directly proportional to what our solubility is. Now, that's scenario number one. Scenario number two is when we have three different salts and they all break up into different numbers of particles. And I want to show you this really quickly, because in this case right here, I'm going to set it up for you. Would you agree that CuS, when it breaks apart, will it not break apart into Cu2 plus and S2 minus? And if we were to solve for a KSP for this, wouldn't it be X times X, or, X squared? So anytime you're breaking apart into two particles, it's always going to be X squared. But what if we did it for Ag2S? I'm going to do this over here. Ag2S, if it broke apart, wouldn't we end up with 2 Ag pluses and 1 S2 minus? And if we set up our KSP in this case, and I'm gonna skip doing a whole ice, maybe I'll do it in here anyway. If we have 0 and 0 here, wouldn't you agree that my change here would be plus 2x and x? And at the end, wouldn't it be 2x and X. And if I plug that back into a KSP for this, which would be equal to the concentration of Ag plus squared times the concentration of S2 minus, the end result is going to be 4x cubed is equal to KSP. So that's different because over here we had KSP is equal to x squared when there were 2 particles. And here we have KSP is equal to 4x cubed when we have 3 particles, right? Well, now let's take a look at this Bi2S3. And again, if we do the mathematics on this, this is going to be Bi3 plus, and this is going to be S2 minus. And if we are trying to figure out how many of each one we want, when we need 3 of this and when we need 2 of this. And if we did an ICE problem for this, we'd end up with 0 and 0, this at the beginning, and then here, wouldn't we gain, 2x, and here wouldn't we gain 3x, and at the end, wouldn't we have 2x and 3x? And if we did the math on this, if we did a KSP problem for this, we'd end up with Bi squared times S cubed. But we'd have to put these values into here, right? So if we put these values in, we're gonna end up with 2x squared times 3x cubed. Now, I don't want to spoil the fun for this, but if we did the actual mathematics on this, 2x squared is going to be easy enough. Isn't that 4x cubed or 4x squared? Here, we're going to have a cube, but wouldn't that be 3 times 3 times 3? Wouldn't that be 27x cubed? Now, I don't want to do any more math here because my brain will start to hurt, but if you multiplied these two together, that our x squared by our x cubed, right? And then we took our 27 by 4, which would be 100 and something, right? You're gonna end up with a lot next to our x, agree? So what's interesting is, whereas on the previous page, we could look and just say immediately, oh yeah, all 3 of these have break into 2 particles, and this right here, the smallest is going to be the least soluble and the largest is going to be the most soluble. Well, they did the math for me here because I didn't want to do all the math all the way out, but they solved for x for all 3 of these things. And what you might expect is, if you look at this here, this negative 73, you might expect a KSP with negative 73 would be the lowest solubility. But when you actually do the mathematics, because it breaks apart into so many particles, check this out. The BIS3 actually has a KSP, or has a solubility of 1.0 times 10 to the negative 15. It's actually higher than the KSP as the other 3. So if we were comparing these, it would be Bi2S3 would actually be more soluble than Ag2S, which would be more soluble than CUS. So what you need to be careful of is this. You can compare KSPs to determine solubility, but you can only do that if they have the same number of particles. If they don't, you must solve for X, and that will determine your solubility. So hopefully this has been helpful for you. The next video we're going to do is we're actually doing some solubility practice problems. Thanks so much.